Hello, hello. All right. Hello, Vicky. Hello, Joel. Hello,
Good
Kate.
morning, Professor. Well, good afternoon.
Good afternoon, Melanie. Awesome. Thank you. That was some voice right there. And Vicky's got some animated avatar right there. And Joel's got some avatar and Caitlin. And now here comes the chat. And we're going to get this rolling. We're going to get this party started earlier. Good afternoon. Aminata, and I owe you something, Aminata. I have not forgotten. I have neglected, but I have not forgotten. I know I owe you something. Just saying. Okay. Good morning. Well, I owe you all things, but I'm not. Anyway, just acknowledging. Okay. Good morning, Gabriel. Good afternoon, Victoria. Good afternoon, Vicky. Good afternoon, Joel. Thank you for being so early. Just acknowledging. Good afternoon, Roger. Good afternoon, Caitlin. Good. Thanks, but a little frenetic. Thank you for asking. And it's going to get more frenetic once we start this class. Thank you. Thank you, Amina. All right, awesome. I actually do appreciate that. And you can even submit for points for the closing the loop that you just did. Good afternoon, Raina. Okay. I mean, there's other people too, but I did Amina. Oh, wow, that's cool. The triple for Aminata. That is a serious animated avatar. Okay. And good morning, Yedaya, if I didn't say, and Roger, if I didn't say, and anybody else that I didn't say. I think that's okay. Oh, oh, I just
Good
lost.
morning, Professor.
Good
I mean,
morning.
afternoon.
Good afternoon. Thank you. Awesome. Good afternoon. Okay. Thank you. Okay. And here comes the other people. All right. We're going to get rolling. I hope I haven't said this to you guys before. Yikes. Wait. I just lost. Hold on. Oh my goodness. I just lost. Sorry. Okay. Yes. Good afternoon, Raina. Good afternoon, Sonam. Wait, there's still people in the waiting room. I see that. Okay. Um, I hope I haven't said this to you before because I don't like to do this too often, but if today is because, yeah, today is Tuesday, but it's Monday, as you know, because you're here. So thank you. Oh, good afternoon.
Good morning, Professor.
Good morning, Fabia. Thank you
Hey,
for that. All right,
that's
that's voice right there. Good morning or afternoon. Yes. All right, good to see you guys. For real. Thank you for the hellos. It's a little crazy because it's Monday to John Jay, but it's not Monday to the rest of the world. And some of us also live in the world, including me. So therefore, two quick things. Number one, well, so I'm going to shut this part. So you have full permission, in fact, request at about
Good
10
morning,
after.
Professor.
Oh, good morning. Thank you, Mohammed. Good morning. Good morning. Awesome. And hello, Anthony. Awesome. Do you guys have permission if to pull, in fact, request at around 10 after 1? Politely tell me in the chat for me to start winding down. That doesn't mean I will let you go at 10 after 1, but I would like to shut this whole party down at 1:20 because like I need time to get to my other thing that happens on Tuesdays in the real world. Um, so we're gonna try to do this whole thing by 1:20. You can give me like a little advance warning at 1:10. Again, that doesn't mean I'll shut down right at 1:10. And I might go to like 1:22 or whatever, but I would like to end us a little bit early, because I need the transition time. So feel free to politely remind me when I start losing perspective on the clock. That's number one. Number two, you may know if you have friends in the other section. I think it's not your problem, it's not your business, but because it's Tuesday, but Monday, the other section will watch. I get, why am I telling you this? Well, normally there'd be two different sections of this same lecture posted in YouTube. So if like you missed something here, if I didn't say it well, you could watch the other section. But that isn't the case today. There's just you, and the other section will watch this recording of you. I don't know why I'm telling you. It doesn't really matter, but just in case you usually like to look for a second version, there will be no second version today. Okay. But then, the coin will be on the other side at some point. Like at some point, you'll have a class canceled and they'll just watch. I guess that's why I'm saying it. Like in fairness, at some point, you'll be released from a synchronized version of the class and you'll just watch their video. Okay. Anyway, that's not, so we're gonna get rolling in a second. What else did I need to tell you logistically? It's still just all very funky because every week soon we'll get into a rhythm where we actually have class 2 times a week. Um, but until then, just bear with me that I still owe you a bunch of feedback and you technically owe a good, valiant, first draft attempt at homework 2 for tomorrow, right? Like that was thanks to Melanie again. That's due tomorrow. A first attempt. You might not be able to do all of it, whatever. Just make a valiant attempt according to the 5-step method. I think I mentioned you do want to put diagrams, even though it seems very mathy and doesn't provide its own diagrams, i.e., I would highly recommend a cosine graph as your first diagram in the homework that's due tomorrow. The whole point of today, once I get rolling, like in a moment, will be to thoroughly finish problem 9 of homework 1. And that should really make it a lot clearer to a lot of you of what it is that I'm looking for in these exercises of a lot of homework 2. Like a lot of homework 2, at least part 1 derivatives, a lot of them are like repetitive exercises that are repetitive and not that bad once you get the main point, but the main point may seem very obscure if you look at it right now. Hopefully by the end of today's class, it won't seem that obscure. So I'm going to get going. If, okay. So I'm looking at the chat, right? Right. Oh, that's a good question. That's a good question. Okay. Great. So someone has looked at, yeah, so someone is saying in the direct chat, like about homework 2, a lot of the prerequisite parameters remain the same, especially for the first part of the homework. So do you have to continue showing all of your works and steps for every question? Great question. So no, you do not. Like anything like that, what's really important, if it's that repetitive, which it is, you're totally right. You want to go really top heavy. Like everything that I'm going to show today until like 1:20 p.m., everything I'm going to show today is like what you want to like drop into my document, into your document, into my desk at the beginning, at the first exercise or 2 of homework 2. Like you want to go overboard to make anything and everything clear in the first exercise or 2. But if you make it super clear, if you even go overboard, like taking some of the concepts I'll do in today's lecture, then right from then on in, you could just keep referring to above, including the diagram. Now, I hope so. Good point. But that's all the more reason why I have spent this long getting to this point is there's like a big bundle of concepts that we need to establish in order to even get rolling on homework 2. And that's true for you. Like when you do the first, I'm saying to the direct chat person, but to everybody, when you do that first exercise or 2 in homework 2, you want to go overboard, really showing me like anything that might be a step is a step. Anything that comes in your mind, like, do I have to write this down? The answer is yes. Like literally, if it even occurs to you as something like, does he want me to say divide both sides by 2 or like whatever? Yes. In the first instance, go overboard. Then from then on, and this is definitely practice for the exam, you go overboard establishing all concepts in the beginning of a document. Then from then on in, now they're so established beyond reproach that now from then on in, you could say see above, see above, see above for sure. But let me also make that clear. You're still saying see above, see above, see above. In other words, you're still always, no matter what, you're always showing 5 steps to everything. It's just that 3 out of your 5 steps might be like one little like see above, or you'll see today too, like you might get to the point where a step 3 of something is so x equals a cosine omega t is the solution to the differential equation, blah, and then you just like use it and move on. But whereas the first time you're dealing with that in a document or me in a lecture, the first time you're like showing why it's the solution. But then once it's a solution, you're saying it's a solution. Okay, so what I'm really trying to say to everybody, I mean, I know I'm getting, but again, I mean, I learned this the hard way in graduate school the second time, is that you always want to acknowledge every single step. If I'm looking for steps, you want to say, here they are. But yeah, they might be as simple as see above, see above, see above, or whatever. Okay, hopefully that, great. Awesome. Thank you for the direct chat. Great. And thank you in the direct chat for you could submit for points for closing a conversation. Like, thank you for closing the conversation in the loop. Okay. So to hopefully that's clear. Okay. Well, I mean, it's clear to one person anyway, I guess. So what I'm going to do now, wait, I'm just fixing the window on the Okay. So got the chat going, got everything going. So what you're seeing on the board right now is like the punchline that I want to get to in a big way by the end of today's class. Like I'm not sync. What you see on the board right now, right, is a spoiler alert. Like that's generally what I try. I'm not saying you already get this. I'm saying this is where I'm heading today. Okay. Um, and how I'm getting there is I'm now finally, hopefully, going to open and close the door on the very last problem of homework number 1, right? So that's where we're going today. And again, for those of you who just joined, please feel free at around 1:10, just gently remind me that I should start shutting the party down. And by party, I'm using that term loosely. So, right, here's our situation again. We've got a mass on a spring constant K, equilibrium position is known as X equals 0. The mass initially starts at a position called X naught. And the question of problem 9, the question is at t equals 1 second, like what is X? At what position is the mass, right? That's the question. Now, before I go, so that's step 2. Before I go any further, let me really make clear that even though that is the question, like that is the question. So I will not really have an answer or something that I can call an answer until I literally get some value of X measured in meters, right? And I've already told you, like the answer is going to be approximately 0.116 meters. Spoiler alert. So when I finally can justify that, that will be my answer. But let's be clear. I'm not spending 3.5 weeks building up to this question so that our big takeaway at the end is one specific number for one specific mass on one specific spring that we made up in our head and we're never going to see again. The real issue is not, is it 0.116 or 0.117 or whatever? The real issue that we're really now trying to solve is, given a mass on a spring in general, what is position as a function of time? That's really the question here. Okay, like that's what it says at the bottom. Like that's supposed to be saying, i.e., what is X as a function of t given the above situation? And what I'm claiming to you is like, that's an important big question in physics in general. That's why we're spending, and it's not a joke. Like, that's why we're spending 3 weeks building up to it. In general, if you have a mass going, if you have something that we're ultimately going to call an oscillator, or perhaps even a harmonic oscillator, something that's going back and forth on elastic material, the question of can you treat time as an input such that we can always predict position as an output or space as an output? Like that's the issue. And the answer is yes, we can. But that's what we're trying to come up with is a relationship between time and space for an oscillator. I'll leave it. Just to note before I go any further. The mere fact that this mass is going back and forth in some sort of cyclical, periodic nature means right from there, I could call this an oscillator. This is some kind of oscillating system. And we're really being asked, can you get a relationship between position and time for an oscillating system like this? Okay. So all of the work I'm now going to do for like an hour is trying to relate X to T. And if I finally can get an equation that treats T as the independent variable and X, oh, you've read that. Okay. Like I want T to be the input, right? Which is known in science and math as the independent variable. And I want to spit out X as an output, which is ultimately known in math and science as the dependent variable. That's what I want once I finally have some kind of equation that relates x to t in that way, then I'll be able to plug in the number 1 for t and it will spit out x and I'll have the answer. But really, I'll really have the answer that I'm really looking for once I have an xt equation. I'm going to say one more thing and then I'm going to move on. You might think we already have it. Well, I think the homework addresses this. Like physics 203, we had equations like this. Like in physics 203, we had like x equals 1/2 at squared plus v naught t. That is certainly an example of what we might call a position time function. X equals 1/2 at squared is an example of the kind of thing we're looking for here. You plug in the t and it spits out an x. Perfectly legitimate example, but it doesn't work for this because, as we've already said, that equation, x equals 1/2 at squared, works when you have a constant a. And that's precisely what we don't have here. Okay, so what do we have here? Let's go to step 3. Okay, step 3. So what do we know in general that might be applicable to the situation? What we know in general, well, first of all, we always know that F net equals MA, right? We always, I mean, it's physics, it's classical physics, so we know that. And I think that does apply here. We also know that the particular type of F that is acting in this situation is the elastic force, the Hooke's law force. So we also know here, right? We know that. Oh, oh, thank you for telling. One second. Okay. Is there anything else we know in general that might be applicable here? Yes, there is one other thing that I know. And I'll tell you what it is, but before I tell you what it is, I'll tell you why I'm going to bring it up. Like, please bear in mind, because I'm going to get into the weeds here. I mean, not by accident, but this is going to get a little bit thick. So it's really important that we maintain the big picture of the forest while we navigate the trees. So remember that my goal is to ultimately get a relation between X and T. The two big principles that I've written down, like one of them involves an X, but I don't see a T anywhere. So somehow, time, I need to know something else about time to bring into this situation. And it would be particularly convenient if I knew some way to relate acceleration to time, because acceleration seems to be the problem here. Like if acceleration were not changing, I would go back to one of my old equations from physics 203. But acceleration is what's changing instant to instant and really ultimately giving me this new kind of challenge. So is there any way in my mind, can I relate acceleration to time in any way? Well, yes. At any given instant, what acceleration means at any given instant. Now not average acceleration, right? But instantaneous acceleration is the instantaneous rate of change of velocity. And of course, velocity is the instantaneous rate of change of position with respect to time, right? So what it is the derivative with respect to time of the derivative with respect to time of, of position, right? And I'm dragging this out, but kind of for a reason. I'm reminding you that what acceleration is the second derivative of position with respect to time. That's what it is by definition. Always. We don't always care, but it's always true. It's a triple equal sign. So I would say these are my three key generalizations that were true even before this problem began. So now let me start analyzing them in the context of this problem. So this is where like a lot of work is now going to happen. Generally speaking, step 3 is where you set the table, and step 4 is where you really begin to eat. And the more intense physics gets, the longer the meals are, so to speak. So step 4, I'm gonna like so step 4, so like buckle, so step 4 is gonna be long, I think. And it's going to be very long for you when you do your homework for the first time or you do the first problem, but then you're going to like not repeat it all the way out, like someone asked me in the direct chat. So what can I say in step 4? Well, I can say, well, all right, let me be even more clear. F net equals ma, always the sum of all the forces equals ma, but here there's only one force acting, only the elastic force, the spring force. Or at least it's only acting horizontally, which is the only direction we care about, because we're trying to solve for x horizontally on the mass. So it's fair to say negative kx equals ma, right? The sum of all the forces is the negative k. There's only one force, so it is all the forces. It's negative kx. Okay, so negative kx equals ma. Then I'm going to substitute in the definition of a that I just established from calculus. So I'm going to say this. Many of you did this homework, which is good. Like this much we can do no matter who we are. And then I'm going to go one step further. I'm going to go one step further because here's a physics strategy. If you're anything like me or any other physicist, you notice that this just started looking a little bit more exotic or complicated or messy, whatever. It's not just you if you think that d2x dt squared is suddenly popping out as like an intense, more challenging part of the situation than anything before. It looked like algebra, now it looks like calculus, right? So what do you do as a physicist when something a little bit harder pops out at you? What you do is you don't run away from that part, you run to that part. You confront it courageously. In other words, I'm now somehow have to deal with like a derivative or a second derivative. So I'm going to deal with it. I'm going to isolate it. I'm going to get it by itself. In other words, I'm going to isolate it, focus my attention on it by dividing both sides by m. And in fact, not just dividing both sides by m, but I'm going to do this other thing that physicists tend to do over, and you don't have to do anything. I'm just saying this is like what we start getting used to as a way of, this is how we deal with, this is what we do when we don't know what to do. Like, I'm not assuming that I know the answer of this yet. I'm assuming that I'm trying to figure things out. So when I'm trying to figure things out, what I tend to do is, first of all, isolate the term that is the new or more challenging term. And I make it a function of variables. So if I'm trying to make a function and relate variables to variables, what physicists tend to do is take all of the constants and group them together and sort of separate them from the variable. So I'm putting or in fact, sorry, I mean, I'm not taking any of that back, but in fact, I would say more like this. Sorry. I mean, now again, this is taste. You could do it the way I just had it, but I'm saying the second derivative of x with respect to t equals negative times k over m x. Like, why am I even writing it that way? How would you know to write it that way? Well, you wouldn't know. You don't have to write it that way. But over time, you get used to writing things that way because by putting the k over the m in parentheses, I'm really trying to emphasize the fact that everything may look like abstract letters right now, but let's try to keep things straight. Like there's different kinds of letters. This is a variable. This is a variable. Also, this is a variable. It's the same variable as the one on the left-hand side, right? And these K and M's, they might be letters, but they're not variables. They don't change from moment to moment or from position to position in a given problem. They stay the same. They are numbers. They just happen to be numbers that I may happen to. They're just general versions of the numbers. They're saying it could be 200 for this spring, or it could be 300 for that spring. I want to write down a relationship that doesn't care which spring I'm dealing with. That'll be true for springs in general. But once I'm looking at a particular spring, whatever it is, whether it's 200 newtons per meter or 300 newtons per meter, it's not going to change throughout the behavior of that spring, right? So in other words, to be as clear as I can be, like this is a constant. I mean, it's a letter, but really it's just a letter standing for some number that I happen not to have specified. But in every way, it's going to be treated as a number. And same thing with the M. And I'm putting them together to drive home the idea in my mind that when I start doing math here, I could say K over M, but really in my mind, it's K over M. Like I could make up some new number that stands for the number K divided by the number M. And that new thing would just be a constant. That entire quantity in the parenthesis is a constant, right? That's part of so that's why I that's why physicists group constants together to like emphasize like, no matter how messy it might look, it's really not that messy. There's just one number that's preceding the x. The x is a variable, the t is a variable. But oh, now wait a minute. Now we're getting somewhere because we only have two variables in this expression now. We only have two variables, and they are precisely the two variables that we're interested in relating. We're looking for an xt expression. This seems to be some kind of xt expression. Let's go a step further. If on the left-hand side, we're taking a derivative of x with respect to t, right? I mean, in other words, if x is in the numerator and t is in the denominator, then this mode of expression, whether it seems hard or easy, this mode of expression is treating the x as a dependent variable because it's in the numerator. It's like a rise. And the t, it's treating as an independent variable because it's in the denominator. It's a run. Do you follow me? Right? Like necessarily in the way that this thing is being set up, we have x being treated as a dependent variable. We have t being treated as an independent variable. This x on the other side is the same x. So all the information that we are looking for is in this package. It's just an intimidating package. Like seriously, remember our goal. I know our goal is to get x when t equals 1, but really our goal is to get x as a function of t. This statement that we just wrote down that I'm going to rewrite on the next page. This statement is a statement that has nothing but x as a dependent variable, t as an independent variable, and a bunch of constants in it. Somehow this statement recognizes that somewhere in the world, if you plug in t, you would get out an x. It's just that this isn't in the explicit form that we want. right? I mean, well, I'm going to move on, but I'm saying we're at an important moment here. This thing has in it, it contains X as it's related to T, but it doesn't tell us explicitly how X is related to T. It's not in a form yet where if you plug in T, it spits out X, but it is in a form that suggests that that could happen, right? So, so, so we're getting somewhere. Yeah, first of all, I guess to be like homeworky or pointsy or grady about this far, I would want you to have gotten on the homework. Or at this point, like as we like this much, I think you could do on the homework, no matter how hard it seemed, or even if it's all new to you, like you can get this far by just doing the steps. Now, what to do next? You'd have to think and do some experiments and possibly allow yourself to make some mistakes or do more than one thing, try more than one thing. Like now we're gonna have to like think in new ways and experiment. But we'll know what to, but we'll be able to start these new experiments now that we've done this much. I mean, I don't want to dwell on it, but what I'm really trying to say is we're now going to solve this. I've had more experience. We're going to get a solution to this. We're going to turn this into an X equals function of T. Of course, I've had more experience doing that than some of you. So I'll be able to explain it, hopefully, or I'll be able to do things now without making mistakes, maybe you wouldn't be able to just do without making mistakes the first time. But they're doable. Like the person who made them up without knowing them in advance. The any more work that I do on the step 4 now is possible because I allowed myself to carefully go through step 1, step 2, and step 3. Like I set it up. So now I know what kind of experiments or thought processes I have to be willing to try and make mistakes and backtrack and horse around with. So that's what you would do. So I'm going to write.
Professor, if you talk so we can't hear you.
Oh, sorry. Thank you. Sorry. Sorry, totally submit for points. I'm not laughing at you. I'm glad you, although the animated avatar just like popped out of me. No, thank you. You should totally submit points for that. The reason I'm laughing is I jumped also because I wasn't talking yet. Sorry, I was just writing something down. I was so deep in thought, I didn't even realize that I wasn't thinking out loud. So you didn't miss anything. Sorry, but thank you. Okay, I'll
Thank you.
talk now. I don't know why that's so fun. Yeah, I was thinking about the math and I guess I forgot there was a class there. Okay. Um, no, okay, and I'll be really honest. Here's okay, well, okay, no, that's great. And also like I'm in a screen view now where I don't see all of you right now. I just and so then that animated avatar just totally like okay, excuse me. Um uh All right, let me tell you what I was about to say, but then I'll also even tell you why I was so lost in thought. Like I'll be really honest about why my head was uh um so like I'm this is gonna start what I'm gonna show you now is new. Okay, everybody like and it's what you'll be it's new enough that involves a lot of practice. So a lot of homework too that you do tonight or that you've many of you clearly have looked at already is like practicing this thing that I'm gonna show you now. Um And it gets easier with practice. It is like a thing. Like it's not an obvious just forward technique. It's kind of a art of science and math kind of things. So here's what I'm saying. We have an equation, d2x dt squared equals negative k over mx, okay? We're trying to get a new equation out of it, okay? We people often think when they start doing physics, oh, physics is about getting numbers, and as long as you know the right equation, you plug certain numbers into an equation, you get out the new numbers. So that people think you get a question. Sometimes people think you get a question in physics, and the answer will come in the form of a number. So the way you solve the question is you use an equation and you plug in numbers and you get a new number. That maybe at some level, at first, that's what physics looks like. But really what physics ends up being is that we're looking for equations. We don't use equations to get knowledge. The knowledge we're looking for is equations, is relationships between variables. Like what we're in fact always looking for in physics is under certain conditions, where will a certain kind of object be at a certain kind of time? Like ultimately in physics, in a way, no matter how far you go, you're always kind of looking for what is the xt relation? What is the space-time relation for a certain set of conditions? The conditions might be free fall, like last semester, like constant acceleration. That's a condition, right? Or it might be like now, the condition is elasticity, like you're subject to an elastic force. What is the space-time relation for that? I'm just trying to emphasize again that equations are often not how we get answers, but they are the answers that we're looking for. Where do they come from? They come from other equations, right? What we have right now is an equation that doesn't tell us x as a function of t. Rather, it tells us some derivative of x. In fact, the second derivative of x with respect to t as a function of x, right? What we have here is what is known as a differential equation. We are trying to solve it. We are looking for a solution to this differential equation. The thing I have to be very explicit about, like as clear as I can be, and the thing I'm going to repeat a lot is we're looking for a solution to a differential equation. We're looking to solve a differential equation. It doesn't mean we're looking for numbers. It means we're looking for a different equation. Specifically, we're looking for dependent variable to be directly, explicitly related to independent variable. That's what we're looking for. And in fact, and always when you solve a differential equation, that's what you're looking for. A differential equation sets up rates of change. And what we're looking for is direct output input. I hope that sort of makes sense so far. Oh, it's okay. Okay. Now, I have to say a couple of things. And this is where I was going in my head a second ago. Like, the hope is that you can join with me in the excitement of finding out, oh, we're about to start learning a little bit about how to solve differential equations. Because we are. Because that is what's about to happen. Because ultimately, really, that's what a lot of physics is about. Ultimately, nature presents us with differential equations, and our job as physicists is to solve them, to turn differential relations into direct input-output functions. That is what physics is about a lot, okay? So the good news is, oh, we're about to do some real physics. We're about nature in the form of a spring just presented us with a differential equation. In fact, technically, it's a second order differential equation because the left side is a second derivative that's being related to some variable. And we're going to solve it. And that's exciting. And it's not a joke. I mean, it's not always easy. Before I go any further, so the good news is we're going to solve a differential equation. The thing I want to make clear before I go any further is you may have heard there's entire classes in math called differential equations, or certainly there are certainly huge topics in calculus classes called solving differential equations. I want to be very clear right now before we go any further. You were not expected to have taken any of those classes or those chapters. I mean, if you did, Quark plus America. That's terrific. But let's be clear. You're about to learn something now, or I'm about to teach you something now. It's not assumed that you already know it. It's assumed that it's the next step in your education and you can do it. Okay? Really. Like calculus 1 and calculus 2 are the prerequisites for this class because it's assumed you know enough about derivatives and integrals that you're ready for us to go this next step in physics and math, which we will. It's not assumed you've already taken this step. It's assumed that you can take this step with me. For real. Okay. Um, uh, so where I was in my head a second ago when like you brought me back to earth is like it's always a dilemma for me exactly when to introduce this word differential equation. It's exciting for some people to see the word and it's intimidating or upsetting for other people to see the word. I'm gonna go on. We're gonna start solving this, but I want to make it clear again. This thing down here is a differential equation. As far as I'm concerned, I'm excited because it's the first one any one of us has ever seen. Like, even if it happens that some of you have seen one, I'm assuming you've never seen one before, or you didn't know it if you did, and you didn't, I'm assuming you don't know what to do with one. So now, and I'm putting myself in the mindset of the physicists like Hooke and Newton. When they first saw this, they had to do something. They never took a class. And like, honestly, calculus had just been in existence for like 5 minutes. They didn't have a class in differential equation. They had to think it through like mathematicians, or even better, like scientists, as we're going to think it through. So I'll write it again. But the only way you can stay with me is if you keep larger perspective. If you bear in mind that when I say we're going to try to solve this thing, sorry, when I say we're going to solve this thing, you have to remember what I mean by solve it. I mean, we're going to try to unpack this equation so that we get x as a simple, a direct, explicit function of t. Once we have x equals blah, 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 t, then I say that's a solution to this. And then we can plug in numbers to get numbers if we want. But that's our goal. Now, I'm just looking at the chat. Okay, okay. Well, okay, okay. It's called second order because what happens to be on the left is a second derivative. Okay, if it were a math class, we might first look at a first order differential equation and get some practice solving that first and then build our way to this. I mean, that is literally what we would do in math class. We're not doing that here because that's not how physics works. Physics, we stumble on the equations that nature, like a spring just is the first phenomenon that we see in nature that's some kind of differential equation. It happens to be second order, so we deal with it, like honestly. But before I go any further, too, why am I calling it a differential equation? Well, yes, there's a derivative in it, but more specifically, Okay. The key here before I go on, what's really making this a differential equation, what makes it interesting and what makes it a puzzle to be solved, rather than a direct procedure to be followed, is that it's not just an equation that has a derivative in it. It's an equation that expresses the derivative as a function of the dependent variable. In other words, d2x dt squared equals negative k over m x is what makes this a differential equation. If that x were a t, this would be an equation with a derivative in it, but it wouldn't be, there could be a direct procedure for solving it. It wouldn't be a brain twist. It wouldn't be a whole class in math or whatever. And it wouldn't have taken us 3 weeks to build toward. If that thing had been a t, and frankly, that, whether you knew it or not, you were dealing with that a lot in physics 203. If you're just told that that some derivative of rise with respect to run is some function of run, that's not a big deal, because in order to get the function you're looking for, you can just do the derivatives backwards, i.e. you can do antiderivatives, i.e. you can integrate generally, right? Now, I'm not saying integration's easy, but if you, so I don't want to get into the rabbit hole of this, but if you're just told, basically, if you're told last semester, V equals AT plus V naught, if you really think about it, you're being told dx dt equals AT plus V naught. You're being told the derivative of position with respect to time equals AT plus V naught. But it doesn't send your mind spinning, because it's relating a derivative with respect to time itself. This is not doing that. This is not relating the derivative to the cause or to the input. This is relating the derivative to the effect or to the output. That's what makes it interesting. I'm going to say one more thing about it. And in other words, I'm trying to justify why we have to think about this. There's not just a direct rule that someone forgot to tell you, or that I should have told you 2 weeks ago. There's not a direct procedure to do to this. We have to think of it as a puzzle to put together, or something like that, or something to reverse engineer, because all differential equations are rates of change being related to the output rather than to the input. Specifically, when you look at, remember what this means in English. We're asking, where is the mass at a given time? And of course, we've been asked that question a million times in physics 203. Where is a brick is falling to the surface of the earth. Where is it after 3 seconds? We're always asked, where is something at a certain time? But in the past, what we always say, if someone says, what's X after 3 seconds? What we always do is say, well, I don't know, tell me the acceleration. If you tell me the acceleration, I can tell you the X. And then back in physics 203 or whatever, someone would say, oh, the acceleration is 9.81 meters per second squared. So then we use one of our equations and we go, oh, okay, fine. As long as you're asking me the X, I say, what's the acceleration? You tell it to me and I plug it in and I get the X, right? That's what we used to do. In other words, if we want to know the X, you just tell us the rate of change of X with respect to T, and we're set to know X. But here, the person says to us, where's the mass at 1 second? And we go, oh, I don't know, but just tell me the acceleration. And I guess I could do some old physics thing and I'll be able to tell you. They say, where's the X? We say, I don't know, tell me the A. And what they say, A, d2x dt squared, right? Second derivative of X with respect to A. I'm going to say this again. They say, well, what's the X? We say, I don't know, tell me the A. And they say, well, the A depends on X. That's what this says. Let me say that one more time. What makes this a differential equation, it's not a coincidence of this, it's not just a special feature of this annoying problem. It is the nature of the beast. That's why we're spending 3 weeks on it. It's just hard and weird enough to be super interesting, but it is just solvable enough to be solvable and to be teachable. So it's a topic. I'm going to say it one more time. The nature of this, of all differential equations, but of this one in particular, is you are asking me, where is the mass at a given time? I tacitly, as a physicist, say to you, well, I could figure that out if you could tell me what the acceleration of the mass is. But then here you say, well, because the mass is on a spring, my answer to what's the acceleration, my answer is the acceleration depends on where it is. So you're asking me, where is it? I'm saying, well, it depends on the acceleration. And you're saying, well, that depends on where it is. That is like circular. If that confused you, you are with me because that's what's confusing about it. The rate of change of x with respect to t depends on x. I'm going to, right? That's what a differential equation is. So the answer to a differential equation is not obvious. Sometimes there is no answer. Here there is one. But how do we get it? Okay, so we seek. So it's amazing that when we can get an answer at all, but sometimes we can. We seek we seek a board that doesn't do that. I never used to do it until I got cancer. I mean, could that be related? That's so weird. Such an awkward thing to say. Sorry, I hope you're not listening. See, this is why I keep my thoughts to myself sometimes. All right, we seek an x, right? Don't forget, what we're seeking is x as a function of t. But what we're seeking an x as a function of t such that if we take the derivative of x with respect to t, we're looking for an x such that if we take two derivatives of it, then somehow we get back x itself times a constant times -1, right? This is like circular. I'm not trying to confuse you. I'm trying to point out what is confusing about this so that we can unconfuse ourselves. Like, seriously, we seek an x, or we seek a function, a type of function, a relation. We seek a function that generates itself times a constant times -1. So times a positive constant times -1 after two derivatives or two differentiations. Like, that's what we're looking for. We're looking for some kind of function which, when you differentiate it and then differentiate it again, you get back to itself, but times some kind of constant times -1. Like, for real, that's what we're looking for. That's what this thing says. We will know, and this again, back to homework 2. Once we get our function, like, we're going to have to sort of guess and put it together from, like, we're going to have to sort of guess into what we are. We will experiment because we are scientists. We might experiment in our mind. We might think about what would happen in the lab and you use that as reference, but we will experiment. We'll picture data that we might have taken in the lab, that you are taking in the lab, in lab 1 and lab 2. We'll picture data and we'll guess and check and play around until we can literally check, until we find a function, a relation between x and t that works. And when I say work, and this is what the homework 2, every time in homework 2, yes, thank you for the reminder. Yes, I totally see the reminder. And yes, all right, so I'm going to start winding. We're almost there. Yes, thank you. And you can keep the reminders coming. I appreciate it. We're looking for a function. Every time in homework 2 where it says, is this a solution to that? It's saying, look at this function. If you took two derivatives of it, would you get whatever that differential equation is saying that you should? Right? Like that's what's happening in homework too. Like it's not calling them differential equations. It's now I am calling them that, but it's just saying given certain, so here we're given the differential equation. I'm trying to find the function that is a solution to it. Then in the homework, it's sort of going backwards of that, or what you might call forwards. It's saying, try this equation. If you differentiate it twice, do you get this differential equation? If so, then it's a solution to it. If not, then not. So here's what we do here. So we're going to guess and check. We right now in the 10 minutes we have, I'm looking to build a function that when I differentiate it twice, I get negative k over m times itself. I'm looking, so I'm going to put together something that I think could work, but then I'm going to test it by taking two derivatives and see if it works. So if I'm in the lab and I have, because I am a scientist, right? I'm not just a mathematician, whatever. We are, if I picture myself playing with masses on springs in the lab, as in lab one or in lab two or in lab two, as in lab one, right? If I hold a mass at a certain position and then let it go, it starts traveling toward x equals 0, and then it travels through x equals 0 to the other side. Or if I just picture the answers I got to homework 1, if I let a mass go from some position x naught, it will go all the way to x equals 0, and as time evolves, and keep going, and then come back and go forth and come back and go forth. And we'll do it in a smooth, simple way, presumably in the lab. So if I picture the lab data, it's going to look something like this, right? And on and on and on. So first of all, I know from math classes what that function is called, right? I believe I have a name for that function. I think it's called a cosine, right? And second of all, so I could picture, oh, cosine might be a good guess here. X is going to be some kind of, I think, maybe cosine of t, but also not only did I, yes, so I see yes, thank you for the reminder. Oh, you didn't see the direct, yes, it's 11. I will wind down in about, I am winding down. We're almost done, honestly, but thank you for the reminders. Yes. I'm saying, first of all, if you've been in the lab and you could just picture the lab data of X being treated as a dependent variable and T being treated as independent, a mass going back and forth on a spring would resemble one good guess for the simplest possible behavior of a mass on a spring would be cosinusoidal. And you could also guess sine, but sine starts at 0, 0. And if you put the mass at the equilibrium, it's not going to go anywhere. So I'm guessing cosine. But the other thing about cosine is, right, in general, and you would put this in your math, in general, if y equals cosine of x, then you know dy dx equals negative sine of x, and you know that dy dx of that d2y, right, equals negative cosine of x. So notice this with only 6 minutes left. Cosine is a highly educated, highly probably correct guess. One, because it actually resembles what I think physically would happen with a mass on a spring, but also because mathematically, cosine is exactly the kind of function we're looking for. We're looking for a function which, if you differentiate it twice, you get back itself multiplied by negative times some constant. In this case, maybe the constant is 1, maybe not. Right? It's got that quality of the input generates the output, which generates input. Again, the kind of quality that a differential equation and therefore the solution to a differential equation has. That thing of I say, what's the X? You say, what's the A? I say, depends on X. Input, output, going back and forth, feedback. Cosine has that quality. So cosine's a really good guess. And I only have like 5 minutes left. But I'm not totally done, because notice I put blanks here. I'm not literally saying that my guess is X equals cosine T, because I'm a scientist. I'm thinking that these numbers are all measurements. Measurements all have units. The units don't work. You can't take the cosine of a second and get out a meter. So I've got to put things in here. So think units. So now I'm going to do this. If you think units, there's got to be something before the t that will cancel out the seconds of time and leave only the units that you're allowed to have when you take a cosine, known as radians, right? I'm saying, I don't know, that should be brackets. I don't know what's going to go before the t, but it's going to be some kind of constant based on the original constants I was given, K and M, right? It's going to be some kind of combination of K and M that are measured in the appropriate units to get rid of seconds and leave radians. Then I'll take the cosine of that on a whatever. Then I'll be left with like, what's the cosine of pi? I'm asking myself, what's the cosine of 0? It's 1. What's the cosine of pi over 2 radians? Oh, it's 0. Is it 0 radians? No. Is it 0 meters? No. It's 0, the number. Cosine just spits out dimensionless numbers. So there's going to have to be something before the cosine that brings back the units of meters so that this whole answer is in meters, right? I've got 3 minutes left. Well, that part that goes right here is almost the easier part. I know I'm building my guess here. I'm building my guess with 3 minutes left. It doesn't prove that it's right. I'm just trying to make something that might be right. I know that cosine values only by themselves range between the number -1 and the number 1. I don't want my values to range between the number -1 and number 1. I want them to range between the number of meters that we call negative x naught to the number of meters that we call x naught, right? Like in other words, in this problem, homework problem 1, I want them to range between negative 0.15 meters and 0.15 meters. So why don't I just take whatever the cosine output is and multiply it by x naught measured in meters, right? In other words, cosine will go between -1 and 1. But then if I multiply it by x naught, then the whole thing will stretch between 0.15 and negative 0.15 or whatever. So the only other question left is, what do I put here? I don't know. Some letter, some constant that stands for some combinations of K and M that I don't know yet, but has to have units of radians per second. I'm going to call it what many of you got off the internet. I'm going to call it omega. I don't know what omega is. It's just a placeholder. I could call it B. I could call it whatever, but I'm calling it omega. So now when I'm guessing, but I don't know what it is. I just know that it is some constant. So this is my guess. My guess that I built from reasoning, from experience and reasoning. I'm guessing that the function I'm looking for looks like this. Which omega is some kind of combination of the K and M constants that somehow makes units come out to be radians per second. Now, this is a guess. I don't know if it's right or wrong. I'm going to go like a tiny bit over 120, like I said, but I'm not going to go to 130. All right, so just bear with me. You will definitely not go late. You're just going to go a little late for early because we're almost done. This is my guess. I just arguing from, and this is how, by the way, also, this is not because you're you and I'm me. This is how differential equations work when you solve them for the first time. At least equations like this, we put them together from experimental reasoning. And then if the solution works, then we memorize it for the future. But there's no way to get a solution without guessing and checking. But the reason we believe them is because we check. This is a guess. Nothing has been proven to be correct here. But now I can check, and this is what I'll do for the last 3 minutes. What does it mean to check? I'm going to take 2 derivatives of this and see what happens. Remember what I need it to be, and I promise we're almost done. Just bear with me. I need it to be the case that once I take 2 derivatives, I get my differential equation that looks like this. So let's see. And I'm going to do it fast, but you can like review your notes, tonight, whatever. So I'm guessing, my conjecture, whatever, was x equals x naught cosine omega t. So I'm going to take one derivative. I'm going to take the derivative of x with respect to t. T is the variable. Everything else on the right side is a constant. So very quickly, if I take one derivative of that, now I'm going to do this quickly. I would drag it out more in your, I'm going to use two rules. One, I know that the derivative of cosine is negative sine. I would write that out as part of step 3 if I were doing this in your homework. Right? Step 3, like if y equals cosine of x, dy dx equals negative sine of x, okay? Then there's another rule I'm going to use right now, which I'm not going to write out, but you write out, which is a chain rule. If, right, I have a function within a function. You may have to go review that or think about it tonight. But the chain rule says if you have a function within a function, you take the derivative of the outside and then you multiply that by the derivative of the inside. So what will I get at the end of the day? I'm going to get this. Negative omega x naught sine omega t, right? I got an omega at the front because the derivative of the inside is just omega. Think about that tonight if you want. But that's one derivative. I do another derivative. So I do this again. Well, the derivative of negative sine is just negative cosine. This won't get rid of the negative sign anymore, like, right? But I do the chain rule again, so omega comes out again. So I get negative omega squared x naught cosine omega t. Now, so what? I promise. It's 122. I'm one line away from being done, whether it looks like that or not. It looks like garbage. Like, who cares? The second derivative is negative omega squared x naught cosine omega. What does that mean? But look, this is what it means. X naught cosine omega t is what I guessed or conjectured to be a long expression for x. Right? So evidently, if x equals that, so I'm writing on the next page and we're done, I promise. So if x equals x naught cosine omega t, then apparently, then the second derivative of x with respect to t evidently equals negative omega squared times x itself. And remember, and I swear we're just about to, remember what we originally wanted. We wanted d2x dt squared to equal negative k over m times x. So what we just established, and this is it, I'm putting down the cannoli and taking the gun. Or the other way around. What we just did was we established so, and I'll flip the pages back for anybody who wants, but of course I'll upload these notes. So evidently, x does equal x naught cosine omega t as long as by omega, what we meant was, well, by omega, as long as omega squared was just another name for k over m. As long as omega squared means the same thing as k over m. Remember we said omega is some combination of k over, we just don't know what it is. Well, now we do. Omega equals the square root of k over m. So that's it. I'm saying thus our solution. So that checks. That means it checks. If you take x equals x naught cosine of square root of k over m times t, if you differentiate that twice, you get negative k over m x. Therefore, that's the solution. So you plug in 0.15 for x naught, you plug in 200 for k over 3 for m. Well, just because I said I was going to go doesn't mean you have to go, but okay, whatever. Right? And you plug in 1 for t, and you'll get, in this case, that x equals 0.116 meters, and that's the answer. But I don't care about the 0.116. I'm saying that's the method. This is the takeaway to that differential equation. And I am done. And we do have to leave. So I hope, so that's it. But I think you can do homework too now, honestly. So thank you for indulging me. So I'm 5 minutes late for being 10 minutes early, but I'm 5 minutes early for being community hour. So I'll see you tomorrow.
Thank you, Professor.
Bye, Professor.
Professor.
Thank you.
Thank you very much.
Bye, Professor.
Bye. Thank you guys. Okay. And I apologize. I know normally I would take questions. I'm going to run, if that's okay, everybody. Yes,